Good day. My name's Todd Cowen, and I'm at Cornell University. Today, I'd like to talk about using infrared imaging as a remote sensing tool, specifically to sense turbulence metrics of environmental surface flows. I'd like to acknowledge my co-author, Dr. Seth Schweitzer, who's done the majority of this work and is giving a companion talk with more details on the technique itself, which you should check out. I'd also like to acknowledge our funder, the primary funder, the Department of Water Resources, State of California. As I tell my students when I teach quantitative imaging, if you can see it, we can measure it. Here I'm looking down from a bridge on a creek that traverses through Cornell campus, and we can see the eddies rising from the bed due to the ubiquitous bottom boundary friction generated hairpin vortices. They form splats on the free surface, or boils as they're often called, and we see those boils advecting downstream. However, in nature, we rarely find uniform seeding, and of course, we don't always have illumination. So we are forced sometimes to provide artificial seeding and illumination, which we would really like to avoid. And it is for this reason that we have sought an alternative through infrared imaging. For this reason, we turn to infrared imaging. Infrared has a great advantage in environmental flows because the surface waters of flows in the environment are always at some disequilibrium with the atmospheric temperatures. And this results in thermal patterns on the free surface in the top hundreds of microns that are due to the latent heat of evaporation and other processes. These patterns have dynamic range on the order of hundreds of millikelvin to several degrees C. And we can exploit those patterns if we have a camera that can see them. And a medium wave infrared imager does a great job of resolving those patterns down to a resolution of about 20 millikelvin presently. And so we get really nice thermal images. The only challenge is those thermal images have both dark or cooler waters and bright or warmer waters that carry information. So we choose to use a mean quadratic difference algorithm because those are able to capture and track patterns that are both dark and light simultaneously, as opposed to the more traditional PIV approach of using fast Fourier transform based correlation techniques. Here we use a fast Fourier transform based MQD technique. I'm showing two images of sediment from an earlier publication to characterize this feature. You see both dark patterns and bright patterns that carry information that we want to track. So how do we capture infrared images in the environment? So what I'm showing is an image of the Sacramento River, and here on the right I have a thermal camera, a FLIR infrared camera, about 1 megapixel, that is aimed obliquely at this region of the flow. Here we have acoustic instruments mounted on a horizontal bar that are hanging into the water. You'll see actually they form a Kármán vortex street, which we'll see in a minute. Piling cluster, a larger diameter that will also shed a Kármán vortex street. And we have ground control points used to georeference the images located in a variety of points, which will become even more clear in the infrared. The left is a drone image showing upstream the region of the flow. We're imaging right down here in the corner. You can see the camera just here. So here's the infrared image. This is a tidally driven flow. Here we're at a modest Reynolds number, and we'll see that we certainly have a strong Kármán vortex street, as I mentioned, coming off these two acoustic instruments. We see a vortex street coming off the piling cluster, a vortex street coming off this anchored pontoon boat. We see eddies coming off the bed in the shallow bank of the river region, but we see in the deeper channel a more nuanced pattern because we haven't quite seen in some regions eddies reaching the free surface, although we do see a new set of eddies arriving now in time. If we look later in the tidal cycle, we see a higher mean velocity and of course higher Reynolds number. And as we would expect, we see a richer, more dynamic ranged set of images that have a higher range of scales consistent with the higher Reynolds number. Let's get quantitative though. That was a qualitative sense of how good these images can be. Here we are in Sutter Slough with the camera now mounted on a boom truck, and we are looking obliquely across this region of the flow. Here we have a tree that's going to cast a thermal shadow onto the flow. You'll see that in a minute. And we have some pontoon boats with ground control points and ground control points scattered on the near shore and the far shore as well. We deployed a FLIR infrared camera with a dynamic range of 14 bits. It has about a megapixel array, and for the size of this array and the dynamic range of about 20 millikelvin resolution, it's a fairly expensive camera, order 100,000 US. Our hope is this cost will continue to fall due to the commercial interest in infrared imaging we're seeing in a variety of industries and scientific fields. We ran the imager at 10 hertz. We used a delta T, or time between images we analyzed, of 0.5 seconds. We'll come back and talk about that again in a minute. We analyzed the images everywhere in a 32 by 32 pixel subwindow. We did not georeference the images before doing the analysis. We georeferenced after. The typical spatial scale is about 0.8 by 0.8 meters. Of course, we're viewing obliquely, so it's a function of where we are in the image field. We ran a Sontec ADV, and we sampled it at 25 hertz. It was positioned about 1.5 meters below the water surface. It's located at the triangular region shown on the image, the red triangle, and it's positioned horizontally within about 1 meter of the infrared imaging subwindow. We have a bit of uncertainty in the surveying of that Sontec, hence the horizontal uncertainty of about 1 meter. The first thing we did is used an RTK, or real-time kinetic GPS, mounted on the camera to measure the position of the camera while simultaneously monitoring the images. And we then used the intrinsic and extrinsic calibration of the camera. And if you're not familiar with that process, I would encourage you to check out Seth's talk, or there's a publication I'll reference at the end which gives all the details. But basically, it's the georeference calibration of the image, the extrinsic calibration, and the intrinsic calibration gives us the pixel by pixel calibration of the array and optical system. By combining those calibrations, we are able to measure with just the images the position of the camera. So here we compare the horizontal X and Y positions of the camera and the vertical position of the camera as measured by the quantitative imaging and the GPS system. And we see the accuracy is incredibly accurate, horizontal and vertical, essentially identical with what we saw with the RTK GPS. And in particular in the vertical, the kinetic GPS has an uncertainty that is about a factor of 5 higher than we see in the quantitative imaging technique. So this gives us really good confidence that our images are well calibrated and that our georeferencing has worked extremely well. So here's the images we see from that infrared camera mounted on the boom truck. Here you see the shadow I mentioned of the infrared, in the infrared of the tree. Here is the pontoon boat with some georeference points. Here's some ground control points as well. In the far field, here's one down in the near field. Those are used to calibrate the images. And here we see eddies in the shallow region of the shore, different sets of eddies in the deeper flow. Let's look at the MQD analysis result. Here I'm showing the processed velocity field. I've subtracted the mean flow, and what you see are the eddies advecting downstream. Beneath, I'm showing the pseudo-colored infrared images, also showing the eddies advecting downstream. Now, if we compare what the infrared system sees and the ADV sees, we see that even though they're 1.5 meters apart, they see essentially the same features in the flow. In particular, the larger eddies are almost identical. They shouldn't be exactly identical because the distance here could be as much as 2 meters apart. The mean velocities look essentially the same. We'll see in the metrics that they are. And in fact, the turbulence characteristics looks very similar. If we go ahead and look at the spectra, we both see a really nice fully developed spectra. I'm now going to remove the ADV so you can see just the IR spectra. I note that the black line is a minus 5/3, so they're essentially both seeing something that on average is about minus 5/3. But if we look only at the infrared images, we actually see that the lower frequencies are steeper, suggestive of a backscatter as the splats rise to the free surface, and we get energy being shifted into the two-dimensional larger eddies of the splats. And we also note that the noise floor seems to be right at 2 Hertz. This is in fact consistent with the delta t of 0.5 seconds, or our 2 Hertz sampling rate. We see that we are unable to resolve any information at frequencies greater than 2 Hertz in time due to that choice. In reality, we did sample at 10 Hertz, and we plan to go back and use a dynamic delta t scheme that would let us play with delta t as a function of displacement. We obviously need delta t to be big enough to have a sufficient displacement, to have sufficient accuracy for the technique, but not so big a displacement that we have decorrelation. And so a dynamic algorithm in these oblique imaging techniques would be a very powerful way to extract both higher information at higher frequencies, as well as ensure sufficient accuracy at the slowly moving regions of the flow. Here I'm showing scatter plots of the horizontal and vertical turbulence intensity. You see effectively they're the same, ADV on the right, IR-QIV on the left. The surface splats seem to have a little stronger shear. We'll see that in the mean Reynolds stress in a minute, but both are characterized by very similar scales. Here are the mean metrics calculated of the turbulence. First of all, I note that the mean velocity in the transverse direction has been forced to 0 by rotating the instrument horizontally in the data analysis approach, so that the mean velocity in the transverse is 0. We did this because of the uncertainty in the surveying, and we didn't have an exact angle of rotation between the two, so we chose to have streamwise dominated results, and that defined our coordinate system. So you see in the streamwise, the two measurements are very, very similar, slightly slower on the free surface, which is not uncommon in open channel flows. We see that the turbulent intensity on the free surface is larger, as we would expect by the splats, but if we shift to a kinetic energy perspective, those splats should be the same, contain the same kinetic energy. It's just characterized in different components. So as the three-dimensional eddy moves to the free surface, absent a dissipative mechanism such as surfactants, we expect the total kinetic energy to be the same, and we see in fact to the third decimal place that it is. Here we see that the Reynolds stress on the surface is about a factor of 2 greater than it is or more than at depth, but both show the same sign and same order of magnitude. So an interesting thing about working with surface turbulence metrics is we can use them to actually characterize the bathymetry. And so Erica Johnson and I, a former student of mine, published a paper back in 2016 that showed the integral length scale of surface turbulence in the lab scaled linearly with flow depth. Here we take the same idea, but we use infrared images and we characterize the autocorrelation of the pixel intensity itself to calculate the integral length scale of the intensity pattern as a surrogate, and a quick rapid calculation versus the using the turbulence metrics themselves. And we're able to calculate the autocorrelation curves as a function of their position across the channel. We can then interrogate this for the integral length scale as characterized by the intensity. So how does the Johnson and Cowen approach work when applied to these infrared images? Well, here we have the bathymetric profile as seen from the bottom tracking ADCP transects. And here is the streamwise length scale from the IR pixel intensity characterized integral length scales. And if we now take the linear scaling of those and compare the two, we see we have a very good agreement between the infrared image measurement and the ADCP measurement. So this is a powerful potential technique for measuring bathymetry and ultimately flow rate from remote sensing techniques. Today I've presented an infrared-based non-contact measurement technique suitable for environmental surface water flows. It allows high temporal resolution, high spatial resolution, and the measurement of the instantaneous velocity field everywhere in the field of view. It's suitable for the determination of turbulence metrics, and in particular allows higher order metrics such as the integral length scale of turbulence to be calculated. I've demonstrated that this measurement can be used to infer the bathymetry of a flow, and this is a promising path to a single camera-based measurement technique of flow rate. We've recently published the basics of this infrared-based technique in Water Resources Research, and I encourage you to check out that publication. Thanks so much for your attention.